And yeah, so I think this is a good schedule for everybody. So yeah, so we'll start out with Ashi, Srikar, and Megha, who basically did a project on Alzheimer's disease and building models for various biomarkers for Alzheimer's. We'll transition then to Yutika and Ben, who have focused exclusively on ADHD. They've been working with the Voiceome dataset internally within NeuroLex and also on YouTube data that Yutika labeled, which super excited to hear. Robert and Madeline did a project on depression. They collected a lot of unique data sets around depression and open source work there. Kind of earlier stage project, but they did a lot of analysis, at least high level analysis, and excited to hear their pitch virtually, and they recorded theirs. TaJah did an awesome demo on obfuscating voice samples to kind of do anonymization and kind of have an identified voice to non-identified voice and kind of still understand the content of the voice. So it's obfuscated and you don't really know who the person is or their identity. So this is a cool security project. Ankita did a keyword spotter for Voiceome, which is important in Alzheimer's disease, and the Boston naming task at seeing an image and saying like the word coconut. So she cited your project. And then Morgan, Sanjanaa, and Kathleen did a project on depression in context of weather and combined with mTurk to get some data. So excited to hear all your projects. Thanks so much for all the time you guys have put into your demos. I've really enjoyed working with you guys. Yeah, and after that we'll go into judging and we'll announce winners of the most. If you guys have any questions about the process post demo day and how we judged, just reach out to me personally and I'll kind of give you a rubric, etc., of everybody's scores. So yeah, with that being said, Ashi, do you wanna start things off? I think you can share your screen and start off presentations.
Yeah, of course. Let's see if I can share my screen. Sorry, just a second.
Yeah, no worries. Take your time. And we also have Jim Harper on the line. He's kind of just there to kind of witness and judge. He's with Sound Health, another company in vocal biomarkers. So welcome, Jim. I just wanted to say who's there.
Okay, can you guys see my screen?
Let me pull off my screen. So yeah, we can see it. Perfect.
Okay, awesome.
All right.
Well, do you want to start off?
Sure. Let's get started. First of all, we're the first demo, so good morning, everybody. My name is Megha Sharma.
I'm Ashi Awasthi.
And I'm Srikar, Ayyalasomayajula.
And today we'll be talking to you about our demo on investigating vocal biomarkers for early stage diagnosis of Alzheimer's disease.
So Alzheimer's disease, or AD, affects nearly 10% of individuals over the age of 65 in the US alone. And 12 to 23% of patients are actually misdiagnosed with AD or dementia early in their lives. This causes a worsening of their principal condition and an overall average of $2.3 billion of excess healthcare costs yearly. And so therefore, a low-cost, accurate test for AD is crucial for early stage diagnosis so that appropriate measures can be taken to prevent significant progression of the disease. So we analyzed two main data sets for our project, the Dementia Talk Bank and an accessible data set. The Dementia Talk Bank is entirely in English, and it consists of 397 audio files of both dementia and non-dementia patients, describing an image in as much detail as they can. The accessible data set consists of about 46 samples, and it's entirely in Spanish. Accessible is a company that NeuroLex has been collaborating with in Spain. So we used a machine learning framework called ALI that Jim created to analyze both the accessible and Dementia Talk Bank datasets. As shown in the schematic, the data is loaded into ALI and then cleaned and filtered in the first stage. Then important features are extracted from the data, which are then outputted as graphs in third stage once the data is fully trained. We use a classification model to classify our data points as healthy or diseased.
The method to create the visualizations based off of the two data sets was actually using a program called TaJah. TaJah optimizes machine learning pipelines using genetic programming. So it searches the data as shown in the CSV file, and the TaJah provides the Python code as shown on the right for the best pipeline to combine and clean features for both data sets to create visualizations. So speaking of the visualizations, an example of the two different correlations that were shown between the two data sets are the heat map and the principal component plot. So the principal component plot clusters the samples based off of their similarity. And as you can see that the larger the data set, there will be a more robust cluster. So that's something that will continue to develop over time, and you'll kind of get to see those correlations a little better. And in the heat map, the closer the correlation is to 1, the data is more positively correlated, as you can see in the linear trend where the colors are a little lighter between the features.
So after analyzing our dementia talk bank data, the following violin plots and feature importance plots were created. Both plots indicate the pause length is one of the most significant features that can distinguish between healthy and diseased individuals. So in the violin plot, it can be seen that the median pause length for the control group is less than the median pause length for the dementia group. And similarly, in the feature importance plot, the pause length has the highest value. We also built a confusion matrix that illustrates the rate of true positives and true negatives is relatively high, and the overall accuracy of the model is 78.7%. The code used for the pipeline is shown below, and a linear SVC, or support vector classifier, is used to fit the provided data. This returns a best fit plane that categorizes the data. From there, you can feed features to see what the predicted class is. So after analyzing the accessible data, the feature importance plots and receiver operating curves are created. So here from the feature importance plot, we can see that the spectral centroid is the most significant feature. In terms of the ROC curve, the closer the solid line is towards the edges of the graph, the more accurate the data. Once more data points are added to the accessible data set, because it only has 46 points right now, the curve will become more smooth and the accuracy will increase. The three most significant features in the accessible dataset were the maximum and medium spectral centroids and pause variability. Just for clarification, the spectral centroid is a measure used in digital signal processing to characterize a spectrum of frequencies. So basically, it indicates where the center and mass of the spectrum is located. So in both the median and maximum spectral centroids, the healthy group has a lower value than the disease group. So here is a violin plot for pause variability, which shows that it was also a significant feature in the accessible dataset. So it's important to note that pause variability was a significant feature in both the dementia talk bank and the accessible dataset. So here's the confusion matrix for accessible, and we can see that there's 100% occurrence of true positives and a 60% occurrence of true negatives. This leads to an overall accuracy of 85.7%. It's also important to note that this accuracy is reached after performing recursive feature elimination, which fits the model and removes the weakest feature or features until the specified number of features is reached. In this case, the number of features was 10, and this was done using the standard scalar function in scikit-learn.
Another idea we had was to create an automatic metric calculation tool that could kind of automate the process of calculating some of these metrics used to diagnose early Alzheimer's and provide recommendations for further testing. So basically, instead of people listening to voice interview samples that are given by potential patients, maybe from the dementia talk bank, from the accessible data set, and manually filtering through them and defining the parts of speech to calculate these metrics, we could use a natural language processing and transcription model in order to make this automatic and be able to do a lot of interviews at once. And so two of the metrics that you can calculate with that are the Brunette's index and the honor statistics, and the figures with violin plots for both of those are shown below. So as you can see, the blue, violins are significantly different than the control ones, which are shown in green, showing that these statistics kind of show a trend towards early onset Alzheimer's or dementia. So the process that we could use to create this tool is to start off by either using a Python speech recognition module or a Mozilla Deep Speech model in order to transcribe these audio interviews, and we'll choose which one to use based on which one gives us the most accurate transcriptions, whether it be to use the already built module or to kind of train our own model. And then once we have the transcription of the interviews in words instead of audio, we can then use the Python NLTK library to iterate through each word in the interview and kind of tag it with a part of speech. And once each view is assigned to its part of speech, we can use the frequencies of filler parts of speech versus actual content parts of speech, and kind of calculate some statistics based on that. And we can present them as metrics in a nice GUI as maybe a feature on Ali, which is a program that was previously discussed, or on Plotly. And based on these metrics, we can give a recommendation for maybe further testing required, or what previous people that have gotten these scores have kind of led to be.
Now that we've shared our progress within the scope of the past couple months, we'd like to share some of our future steps. So we've received an updated accessible data set from Jim, and we're going to work on filtering that the same way that we've kind of discussed with the data shown. And we'll be training a model on the dementia bank data set and determining if that accuracy still holds with the accessible data. So given that they're in different languages, we're answering the question is if that 78% accuracy holds across languages. The other step is to increase the number of features on Ali, as previously discussed, and some techniques to do that would be with augmenting data with more samples and establishing new cleaning techniques. Our end goal is essentially to publish a paper in the Journal of Alzheimer's Disease and Dementia. The deadline is in December, so our team will be working until then on these future steps. So we hope to have had an impact on NeuroLex by furthering the relationship with accessible and proving that the accuracy of the test is not compromised over different languages, which is something we'll definitely be working on in the future to use the results to differentiate NeuroLex in the ADDF Grant Diagnostics Accelerator. And we have proved that the pause length is a significant vocal biomarker that can indicate dementia, which can be used for future applications. But just as we hope to have had an impact on NeuroLex, NeuroLex has definitely had an impact on our personal growth.
So for me, this was my first exposure to machine learning techniques. And before this project, I never even used GitHub before. So I was very new to all this. So I learned how to filter and handle large data sets and also extract important features.
So a quick shout out to Jim. He gave us a lot of really great data visualizations that we were able to display in this PowerPoint. And as someone that's very interested in data science, the introduction to kind of how these data visualizations come about and getting to see how they're built up from scratch instead of just seeing like a shiny plot that magically appears at the end was a really great experience.
And for me, I'm familiar with the more computer science, and this is my first time kind of using that in the more medical and biomedical field, and learning how code can also have an impact on these other fields. And I also learned a lot about Alzheimer's and dementia and what goes into diagnosing those and the different types of tests and metrics you can go through to get a proper diagnosis.
So that is our presentation for today. We'd like to thank you all for listening this early this morning, and we would like to open the floor if we have time, or if not, please reach out to us with any thoughts or questions that you may have. Thank you.
Awesome, guys. Thanks so much. Yeah, so I think we're kind of a little over, so I'm gonna keep going, but I will definitely follow up with some questions afterwards. I really appreciate you guys doing the demo, and really it's been a joy working with you guys. So
Thank you.
Thank you.
Cool. So so we're gonna keep moving. The next presentation is Yutika and Ben. So I'll open the floor to them. You guys can definitely share your screen and start right now.
All right, just give me a second. Can you guys see this?
Yep, can see it.
Perfect.
All
All right.
So our presentation was about utilizing voice analysis to diagnose ADHD. My name is Yutika. I'm a sophomore studying biology at UT Dallas.
And my name is Ben. I'm a sophomore studying computer science at Miami University.
So ADHD is an extremely common neurobehavioral disorder with an overall prevalence of 4.4% in adults. However, even though ADHD affects all sexes, races, and socioeconomic statuses equally, there's still a very large disparity in the prevalence of diagnoses between groups. And overall, ADHD is extremely underdiagnosed and misdiagnosed. In fact, more than 20% for a number of reasons. Number one, because current diagnostic tools usually consist of things like self-report skills or other very subjective tests. And second, diagnostic criteria for ADHD in the DSM were actually initially developed for children. And lastly, adult ADHD often occurs with other comorbid conditions that mask the symptoms of ADHD at times. And on average, this entire process for evaluating and diagnosing ADHD costs more than $2,600 an adult, and over a period of 6 months, which can be greatly reduced with an easier, more cost-effective, objective diagnostic approach. And untreated ADHD in general also have very high costs to both the individual and just overall economic output. And overall, it's estimated to cost America a total of $42.5 billion a year. And since there are currently no known patent studies or diagnostics related to this, and almost all current research on ADHD is directed towards children, we really wanted to bridge that gap in the research field and within NeuroLex. So our main goal for this demo was to develop an early stage model for the early diagnosis of ADHD.
So between Yutika and myself, we had a bit of an interesting approach to this. I was more focused on the data science end, and she was focused on the research end. So we kind of did two parallel projects. So I'll first talk about the data science portion. So for this, I collected data from the Voiceome data set, just about 2,700 data points. All of them were labeled using the adult ADHD self-report scale, which, as Yutika talked about, was self-reported. This is the question that we analyzed. It was describing this picture in detail, and we thought that this would capture ADHD because someone would either become really focused on one particular detail, or they would start drifting around from one place to another without really getting into any depth there because they would have that kind of thought drift. So after collecting all of the data, we had 6 different libraries for a total of 826 features. And after getting rid of some data points that didn't properly load and everything, we just had about 2,100 data points. And then after some synthetic data making for the minority class, because we only had 332 people with ADHD in those 2,100 data points, synthetically oversampled that up to 498 and then balanced the majority class down to 498. So it had just about 1,000 data points to use. I didn't get to do a lot of those fancy graphs because all of those models were starting to do pretty poorly, actually. Just about 45% accuracy on a logistic regression model and on a support vector classifier after full 10-fold nested cross-fold validation. So it's not doing as well as a coin flip even, but that just might be because of this particular fold on this model. So then I tried it one last time because maybe when I was using smoked or synthetically oversampling the minority class, it was actually amplifying noise, but without smoke, it only did slightly better at 45.9% accuracy. So it looks like it wasn't doing so well. So I had one last ditch effort where I did a 2K factorial analysis, which just basically tells me how much each library or each bundle of features contributed to the output, as well as combinations of libraries. And I found out that the SOX library contributed the most at about 8.4%. So then I reran a nested CV with just the SOX library, and it ended up being just about the same with about 44.9% accuracy. So then I had 6 different reasons that I kind of think are why the accuracy wasn't so high. 1, obviously not enough data. You can always do better with more data. 2, improper features. Maybe we just weren't looking with the libraries in the right places, and it wasn't capturing ADHD very well. We largely focused on vocal features and simple linguistic features, but didn't really do any transcript analysis, which definitely I think would have helped because it would have kind of shown what subject someone was focusing on. Improper method to elicit desired features. Maybe this just wasn't the right question to be able to find this out. Wrong patient group refers mostly to the fact that all the research that Yutika and I found was focused on adolescent ADHD, and most of the data points we had were not from children. So maybe the signals are just stronger when you look at younger children. 5, improper classifications. That one just comes mainly from how I labeled the data. Because it was on the self-report scale, there's a certain point value on that scale that will put you into the ADHD category, as it were. But someone who has, say, the minimum score and the maximum score for being in that category would be both labeled as ADHD in this case, and there wasn't any accounting for severity because there wasn't enough data. So the signals might have become muddled because of that. And then 6, the signal just might not exist, though I'm a little skeptical to say that because of what Yutika did, and I'll hand that off to her to tell you about.
So on the research end, we collected another data set by getting 200 YouTube audio clips, 20 seconds each, and inputted them into a template with labels like gender, location, audio quality, and whatnot. And I then used Prot, which is an open source software program, to label features that I found were important from other studies that looked at voice markers in children with ADHD, and I imported them to the spreadsheet template I used before. I then conducted a t-test and found that fundamental frequency and intensity were higher in ADHD patients, which is consistent with the children from ADHD, which indicates that the same vocal biomarkers are present regardless of age. I then sent this data set over to Jim, who ran a machine learning model against it with over 600 features, and found that males achieved 77% accuracy, while females achieved almost 100% accuracy. And when combining both to create a gender model, it reached 90% accuracy. So the impact that this demo has by creating an efficient question or a model to diagnose ADHD is that it will, severely decrease time and costs involved. And it can also serve as a more objective means to diagnose so that underrepresented groups won't just go undiagnosed. And in NeuroLex specifically, we were able to increase the number of labeled speech samples, and ADHD in general wasn't previously looked into. So we were able to start the pilot for that so the future tribe members can build on. And the models we've created and our findings can just serve as objective data to customers to show that the technology and the approach used by NeuroLex works, especially if we're able to get a research paper out of it in the future.
So then on top of the contribution to NeuroLex had a contribution on us. I personally got more experience using a lot of those libraries. All those scripts that I did for all the nested cross-fold validation and factorial analysis I wrote myself. So now I have a library of those different scripts ready to go on my next machine learning project, or even on continuing this one.
And for me, this was the first time I had the opportunity to construct and take part in the design of a demo from start to finish. So I learned a lot from that, from conducting literature reviews, ADHD as a whole, just being able to work with voice data and learn about different features. I also learned how to use Prot, and I started learning Python and machine learning techniques, which I definitely hope to continue over the next few months so that I can participate in the data science aspect as well.
So then as this project continues, Yutika definitely found a signal that I just didn't find in the data set that I used. So we're hoping to use that idea to create a new question within the Voiceome data set that might capture this better, or at least find a better question or analyze the question better. We're just not really sure. That's something we want to focus on before we're able to publish a paper, is getting that ironed out with the Voiceome data set and staying involved with NeuroLex and Jim.
So thank you to Jim, our mentor, the rest of the NeuroLex team, and the rest of the tribe members. This was an amazing opportunity, and we cannot wait to continue.
Thank you very much. And that's everything for that.
Awesome, guys. Thanks so much. I think this was an awesome area to explore in ADHD, and I think you guys had a pretty thorough analysis on both data sets. Just one quick question. Mm-hmm. Do you guys think expanding the YouTube data set would make sense here to maybe make it bigger, given the signal that we found, and then test that on the Voiceome data set itself?
Well, what I first realized is that there's a lot of data on YouTube, especially with ADHD, since it's so common. So I definitely think that it's possible to increase the data set, and then definitely compare it to Ben's set, because that was our original plan. And then since Ben's data set didn't achieve the highest accuracy, we decided to push that off until later, but that's definitely a future plan.
Yeah, no,
Yeah,
I love that. Go ahead, Ben. Go ahead.
I additionally think that one of the problems we ran into is the self-reporting of ADHD. So when you have people on YouTube who have more than likely been diagnosed with it, they have a much stronger case for, hey, I definitely have ADHD. And you don't run into the problem of someone who, is like, I'm not really sure. I guess I'll answer a 3 to this question instead of a 2. It gives a much stronger signal because people who are definitely more likely to have ADHD than not.
Yeah, that's like one of the lessons here, I guess, too, from the data set. So I'm excited to see perhaps if we could auto-label the content of that from the Voiceome with the model in ADHD, and then relabel it and perhaps extract a larger signal, which would be super cool to see. So cool, awesome, guys. Thanks so much. We'll move on. Next is Robert and Madeline. They have a video that they recorded, so I'm just going to play that video. For this, it's a shorter video, so we should be able to stay on time here. So I'm gonna share my screen. So this was their video, in case you guys want to watch.
This is Robert, Schad, and Madeline Mullen with NeuroLex Tribe 5, and our project was improving voice diagnostics for depression by analyzing novel features.
So the main problem we wanted to focus on is that 264 million people have been diagnosed with major depressive disorder throughout the world, and there are undeniably millions of more cases that have gone undiagnosed. Suicide is the leading cause of death in people between the ages of 15 and 29, with about 800,000 deaths due to suicide worldwide each year. This is a severely urgent issue, and with current methods of diagnosis being expensive and subjective, there are many cases that go undiagnosed and many suicides that occur as a result of a false negative diagnosis. So therefore, we wanted to create an objective method of diagnosing major depressive disorder to highly optimize diagnosis in terms of cost effectiveness and success rate, and suicides can be prevented for those who go undiagnosed. So a few of the goals for our demo that we wanted to achieve were identifying acoustic markers of depression, collecting data from DIQUAS and MHH datasets, creating a trainer model using Python audio analysis, testing the trainer model using depression YouTube datasets, and learning and developing our coding skills along this research demo.
The solution we developed began with working on training a model based on the depression voice datasets, the DIQUAS and MHA datasets. And then we test the depression My Story YouTube videos that are all over YouTube against the model to determine how accurate the model was and how effective it is to apply the YouTube videos to this model. And so by determining the successfulness of the YouTube videos in being tested against the model, if it's successful, an inexpensive and objective means of diagnosis can be refined and developed in the future. And the outcome and future directions for our demo. So in the future, we plan to determine the successfulness of testing the YouTube videos against the dataset trained model. And then after this, we can refine a method for using the YouTube videos to be tested against the model. And this would provide an efficient and accessible method of objective depression diagnosis.
So a little bit more about our personal goals and what we've kind of learned over the summer is I definitely have gotten more interested in computer science. So I really want to explore more courses related to computer science within the University of Cincinnati. And I really want to continue improving my Python skills because I feel like this project was just the cusp of the opportunity Python provides. And with that, expanding my experience within the biomedical field, I really want to learn more about how I can apply computer science to biomedical, which I'm really excited about, and I hope you guys can find me on LinkedIn. So overall, the summer was a really cool experience. I'm definitely more interested in learning about computer science.
And some of my personal goals, I'd like to continue refining my programming and data science skills. This was my first taste with data science and my first true taste in programming. So I'd like to continue learning more and exploring applications, especially in the biomedical field, for computer science and data science. And with that, I'd like to expand my experience within the biomedical engineering field, especially as I move throughout my undergrad degree. And just like Maddie, you can find me on LinkedIn. The link is on this LinkedIn dot there.
Yeah, and we just want to thank you all for listening to our project. And if you have any questions, please reach out to us. So we had a lot of fun doing this over the summer. So thank you all for listening.
Cool, thanks guys. Yeah, so Maddie and Robbie got access to a lot of these data sets. We're kind of in process of putting them all together according to their plan. But I think this idea of taking YouTube data, data sets from like clinically annotated labeled data with depression, like the PHQ-8 scores from DICWAS, and also combining that with some other intermediary data sets and then testing it on other data sets could be really cool. And I think we're in the midst of moving forward here. And I think this might be an area where you can collaborate and grow the depression data set. But I really appreciate you guys' time, effort, energy as well. And looking forward to continuing the project post demo day. All right, so let me just go out back. So next demo should be pull up the demo day presentation again. So next demo should be here. TaJah, so I'll let you share your screen. You're still there, right? Still have access. Cool. All right, TaJah, go ahead. Go ahead. Excited to hear your pitch.
Let's see. Can you guys see my screen?
Yep, we can see it. It's
okay,
there.
cool. So, hi, I'm TaJah. Over the summer, I was developing voice obfuscation software for SurveyLex, basically to enhance the anonymization options for the users to protect their privacy. So our problem was that audio responses that SurveyLex was collecting was containing sensitive user information. And so I developed some software to take these audio responses and modify their tone, pitch, and frequency to be able to preserve their identity, I guess, so you can listen to the files without really getting a sense of who the person is. So I don't know if this will work if you can see my desktop, but I have the files put up here. If I can,
I don't think we see your desktop, but we can see the Google. Okay, now we can. Cool.
Okay, cool. So yeah, so here I have two audio files that I'm gonna obfuscate with this. And it should run up here, and you'll see the files get mutated. Okay, so yeah, so we started out with the 0 and sample files, which were both mutated with frequency shifts, both up and down for both files. I don't know if you'll be able to hear them if I play them, but I mean, they're all the same, just shifting their frequencies to preserve that identity. So moving forward, I'd like to, instead of just shifting their frequency, to implement the tone and pitch as well. I just haven't done the research onto seeing how that actually affects the voice and if it's still intelligible after transforming those properties. Also, I'd like to try to censor certain information using keyword detection. So if they're going to say their name, birthday, address, or any of that, it'll automatically take out or beep out that part of the audio file. That way, even when you're listening back to it, you won't be able to hear it. So this impacted NeuroLex because it offers anonymization options to the SurveyLex software to protect the user's identity, which may give them more of a sense of privacy when they want to share that personal information that they're giving us. And for me, it was my first time working with voice data. So like I said, I hadn't done much research into how the tone, pitch, and frequencies were affecting the voice files, but through testing, I was able to get some intelligible modifications. And I'd also like to use some transcription software to make sure that the integrity of the audio is being preserved as we move forward. That way it's like for sure intelligible, and you can still actually use the responses that we're collecting through SurveyLex. I was also my first introduction to neural networks. I didn't implement any in this demo. However, I'd like to moving forward, as neural networks in voice obfuscation and anonymization are state-of-the-art technology. So I'd like to take some inspiration from those methods and implement those moving forward. And yeah, that's everything I had. Do you guys have any questions for me? All right, well, that's everything.
I'll ask a quick one. So
Okay, yeah.
Is there any way you could play the audio just to see if we can hear it? I'm kind of curious. I think everyone would love to hear the pre.
I don't know if you'll be able to hear it, but
did you play it? I don't know. Guess we.
Yeah, were you able to hear it?
No, we weren't. All right, it's cool. But yeah, I think this is a really cool project. I think when we looked at the literature, there aren't that many papers out there on obfuscation of voice data.
Right.
So this is kind of like the first step. I'm kind of curious, like, what do you see is like the ideal ideal obfuscator to be state of the art, like on a SurveyLex product? Like what would be the ideal deployment for this? Like, would you see like somebody clicking a checkbox to opt in to obfuscation, like on the survey? Or how do you see that? I'm just kind of curious your thoughts there.
So it'd be something like that where they opt into the anonymization, and then when I don't know how you're storing the files or anything, if you're just sending them straight to like a database, but passing it through the software as soon as it's collected, so it doesn't have a chance to be heard by anybody, potentially like threatening that anonymization that they opted into. Just passing it through that software and then sending it to the database beforehand would be my ideal process for doing that.
Gotcha. Okay. And would you see like a neural network potentially be useful to just almost like encrypt like pre-post to a random voice among a bank of voices? Is like an ideal next step here?
Definitely. So like I said, I didn't implement any of the neural networks just because like they're tough to get into. But it was my first introduction, and moving forward, I'd like to start implementing some of that because there are papers with neural networks, and they're training to recognize the voice feature set that makes the voice different from, I guess, other voices. So they actually have done the research into finding what needs to change or be preserved. So for me to be able to do that and put that into the software would be probably my next step.
Cool, man. Yeah, no, this is great. I'm really excited about this area. I think it's like a really cool area to explore, and there's a lot we can move forward with here and just kind of build new stuff and kind of build more demos around. So I really appreciate you kind of delving into it. And
yeah, thank you. And also, if you guys did want to try it out, I have my GitHub here. You guys can go, and I have comments in the code where you can just see how to run the software. It's super simple. Yeah, that's everything for me.
Awesome. All right, let's keep going. Appreciate it. Next is Ankita. I'll let you take the floor.
Okay. Awesome. Can everyone hear me?
Yep.
Okay. Okay. Hopefully this is in presentation mode for you too.
Yep, we can see it.
Okay, awesome. So the title of this project was creating a model in Python to identify keywords for the Boston naming test. So this was essentially a research and data science demo hybrid. So that's how I came into this project. So we tried to collect the data, clean the data, model the data, and then test and summarize the performance of the model. So with this, what actually happened, just to give context before I dive into everything else. So we collected data from the Voiceome dataset and then attempted to clean the data via deep speech. However, the accuracy was not enough. So a cleaning script was created and the data was manually annotated for training. And with this, for simplicity and for demo day, we chose one keyword. So we essentially built a keyword spotter and modeled the data using Ali and Teapot. So to give some context, what is the Boston naming test? The Boston naming test was created in 1983 to measure word retrieval in individuals with language impairments. And this can arise from anomia or aphasia from Alzheimer's, stroke, or other forms and causes of dementia. And the goal of the Boston naming test is to spot a keyword, which is a specific target word in utterances. And patients and subjects have difficulty with some words when compared to others on the Boston naming test. So a typical Boston naming test will consist of 60 black and white images of objects. The patient or subject must name the object, and the researcher codes and marks how accurately the object is named. To provide more context, many aphasias result from damage to the left hemisphere, and this can be rather complex. Damage to Wernicke's area causes speech comprehension and understanding impairments, and Broca's causes speech production impairments. The problem. Interestingly, no machine learning model exists to automate the scoring of the Boston naming test. However, there's a host of literature on machine learning neural networks and keyword spotting using those specifically. And our team proposed that the challenges in detecting multiple keywords in the Boston naming test can be overcome through an algorithm. Let's first define some terms quickly. So machine learning is a study of using algorithms to find patterns in massive amounts of data and building models that improve through experience. A neural network is essentially a network inspired by actual biological neural networks, and it's designed to recognize patterns. A recurrent neural network is a class of neural networks that allows previous outputs to be used as inputs while having hidden states. And a convolutional neural network is mostly used for image recognition using layers of neural nets. So the goal for our intended model was to score the Boston naming test with at least 95% accuracy. And with this intended model, clinical observers would have no longer had to solely score these utterances, which would have decreased overall subjectivity within the Boston naming test. And our team, based on definitions on the prior slide, our team was going to focus on recurrent neural networks rather than convolutional neural networks, as we were analyzing voice data over a small period of time. And we would have wanted to build two separate male and female models or create male and female classes within one model. So for our data set, we use the Voiceome dataset consisting of various keywords, and to address bias, this dataset is very large and encompasses many health traits. We also chose the keyword coconut and split the data into male and female folders. Data cleaning. So again, I mentioned that deep speech, the open source speech to text engine, only had 50% accuracy in translating the word coconut. So a cleaning script was created to focus on one word. And this script was essentially designed to categorize data with a simple yes or no. And through this, I manually categorized 235 coconut and 235 other for an even training data distribution. And for our model, we use data from the female folder specifically for this demo. So for modeling the data, Jim sent in wonderful data visualizations from Ali, which is his framework for building machine learning models, and using Teapot, which is a form of genetic programming, as you can see here. So Teapot selects the best pipeline. Important features for this model included onset, rhythm, MFCC, which is essentially the short-term power of a sound, spectral centroid, spectral bandwidth, spectral contrast, flatness, spectral roll-off, zero crossings, and tempo. So the most important with the feature within PySpeech was the standard deviation, MFCC standard deviation, and with Librosa, it was tempo. And as you can see, Coconut was much more distinct than the other class. So with the tempo, you can see Coconut. So that's just a nice data visualization. And thank you, Jim, for sending those over again. And as you can see here, the receiver operating characteristic curve for the PySpeech features was closer to the upper left. So that indicates that the model generally performed well. And using the PySpeech features, the model performed with 86.3% accuracy. And as you can see here with the confusion matrix, the true positive and true negative rates were high. And this is just an example. This is just a model that was extracted using the PySpeech features. So Teapot chose extra trees classifier, which is essentially an installable learning method based on decision trees. And for Librosa features, as you can see, the receiver operating characteristic curve is not as nice as with the PySpeech features, and the confusion matrix rates are still high, but not as high. For future directions, we want to build a model for a specific Boston naming test with multiple keywords, and we want to optimize the model by analyzing .wav files backwards and forwards. And we also want to optimize the model to better suit male and female voice distinctions instead of just analyzing data from one folder. In this case, we chose the female folder. We also want to dive deeper into features such as age and language. So for personal growth, again, my name is Ankita Moss. I just graduated Emory. I was a neuroscience student and had a minor in ethics, so very different from this. But I have a huge interest in machine learning, and thanks to this project, I'm looking into gaining a machine learning certificate, looking into different programs. I hope this really benefited NeuroLex and that maybe this project can continue and future tribe members and myself can come together to build upon this and really work on those future directions. But this project really impacted me in a huge way because I have a greater understanding of what machine learning is, and I had a huge introduction to Python solely because of this project. And I want to say a huge thank you to Jim for letting me hop on the team later in the process and for meeting with me literally every week to ensure I was learning and hitting my goals and providing all these data visualizations and always answering any email or question I had. So he was an amazing mentor and has really inspired me to continue on my journey with Python and machine learning. So that's the end of the project.
Awesome. Thanks so much, Ankita. I really appreciated you going through all that. I'm really excited about this automated keyword spotter for Boston naming. There's so many other words we can analyze, so many more things we can do. And this was a great start. I think annotating this data and getting more words to annotate in future tribes could make it so that we can connect it all together into an automated system. And I'm really excited to kind of continue this and really appreciate all the work you put in as well. So
thank you for being an awesome mentor.
Yeah, totally. Cool. Awesome. Well, we'll move on to Morgan, Kathleen, and Sanjanaa, last group here, and excited to hear what they have to pitch.
All right, so let me share my screen.
Is Morgan on here yet? Because it's 3 minutes until 10:50.
We can wait till 10:50 if you guys want. Not a problem.
I'm texting her. See you.
I think she's on, right?
Okay. Morgan?
Yeah, she's there.
Okay, cool. All right, so our project is improving voice ML model for depression by analyzing novel features, and I'm Sanjanaa.
I'm Kathleen.
And I'm Morgan. There is no simple objective test on the market to diagnose depression. An individual is typically diagnosed via a questionnaire, Patient Health Questionnaire 9 or PHQ-9, but the lower accuracy and the ambiguity surrounding solely qualitative diagnostic tests causes uncertainty and great difficulty for individuals to get the correct diagnosis and treatment. At NeuroLex, we're trying to create a more quantitative test to diagnose depression by analyzing voice features through machine learning models.
Next slide.
Here shown in the table are new and repeated features that we considered in our project. The PHQ-9 is the standard diagnostic test and is found to have a sensitivity of 88% and a specificity of 85%. Headaches have been shown to influence speaking, speed, and articulation. Menstrual cycles and birth control have been shown to influence voice pitch. Emotions were considered because the range of emotion in voice could be used to detect depression. Weather is known to affect mood, which is evident through seasonal affective disorder, also known as seasonal depression. And pollen affects allergies, which in turn can affect the voice.
Two things that are also unique to our project is our use of music and GIFs in our survey questions. The categories for our audio questions were speaking freely, describing something, and reading something. It was in our audio questions that we accounted for ranges of emotion in people's voice. Next slide. We found participants primarily through mTurk, and we also created a website with a description of our project and links to our 3 surveys. We shared this website with mental health and university Instagram accounts and Facebook groups, and we also gained coalition members who are interested in receiving updates of our project's progression via email. Anyone was allowed to participate in our study, and the main requirement was to take the surveys on different days within 2 weeks after finishing the first survey. Next slide.
So we modeled our data using scikit-learn to create a supervised machine learning model for 2 classes, depressed and non-depressed. So because our non-depressed class is much larger in terms of data than a depressed class, we randomly selected data to create a balanced classes of 14 participants each. And then using LaBrosa, we featurized our data sets. So as you can see in figure 1, there's the 2 features that are distinctly different between the 2 classes are the loudness SMA3 mean falling slope and the loudness SMA3 standard deviation falling slope. So these are 2 features that we're definitely going to look further into once we acquire more data. And figure 2 and figure 3 here depict that visualization that there are significant differences between the 2 classes for these 2 features of loudness. So after featurizing, we created a machine learning model, which is a logistic regression supervised machine learning model. And we can see in figure 4 here that our model is excellent at detecting whether an individual is depressed, but it's not as accurate at detecting other. But our RC curve is promising because it demonstrates that our model is able to discriminate between the true positives and the false positives very well. And then figure 6 here, we can see that our model is 75% accurate at determining whether an individual is depressed or other.
For research features and action item next steps, we want to potentially consider the amount of interaction with sunlight, as light therapy is a treatment known to help combat depression. We want to look into weather over a time period and the kind of moods the weather encourages by categorizing different weather types in different ways. By applying for grants, we obtain the capital needed to obtain more resources and more participants. For potential future survey feature next steps, we want to potentially consider the time participants spend alone, their resistance to suggested activities, and deteriorated performance. We want to look into socioeconomic income and income status and demographic questions, as they can be indicators of research accessibility and data set diversity. It's a common misconception that mental illnesses like depression aren't physical disorders, but depression occurs in the brain and often manifests themselves through symptoms like muscle aches, headaches, stomach aches, and other physical symptoms. For data machine learning feature next steps, we'd use imbalanced learn and SMOTE to more accurately analyze our current data set because our set is rather imbalanced. We'd use analyzing text features like parts of speech using Ally ML framework with NLTK and space features with LaBrosa embedding. And finally, we want to use voice analysis to see the menstrual cycle and the weather's effect on depression. Next slide.
Our impact on NeuroLex includes the use of features that had not yet been used in a tried project before. Accounting for these features and their effects on voice diagnostics would further improve the accuracy of a machine learning model that is intended for diagnosing depression. The use of GIFs and music in a SurveyLex voice survey has also not yet been done before in a tribe, and results from these questions may provide new insights on participants' vocal reactions to different forms of media. We also advertised NeuroLex by creating a website about our project, and we gained coalition members who are interested in our research. Next slide.
I'd like to thank, I'm Morgan Gallimore. I'm a rising third year at Georgia Tech studying biomedical engineering. I'd like to thank Jim for being a great mentor and the NeuroLex team for welcoming me to the team of the companies whose aspirations are so akin to mine. During the fellowship, I learned about the technical side of medical research, about recruiting research participants, and to improve my planning skills. I look forward to what we do next.
And I'm Kathleen. I'm a rising senior at Michigan State University studying computer engineering. And I just want to thank you for welcoming me back to NeuroLex. And since the last time being in a tribe, I think my planning skills have improved a lot, considering that my last project was nowhere near as far along as this one. And this was my first time using SurveyLex, so I learned about ways to gain and work with participants. And this was also my first time making a website, and I learned more machine learning techniques. Overall, I think there were a lot of great skills I learned during this study. Thank you.
And I'm Sanjanaa. I'm a rising junior studying CS and entrepreneurship at Rice. And I just want to say thank you to Jim and NeuroLex for giving me this awesome opportunity to innovate in the health tech space and work on a really high impact project that can help individuals more accurately diagnose depression. I've learned so much about the research and innovation process, from coming up with an idea to actually pursuing it with this team and creating a survey, recruiting participants, and obviously the really, really fun part, which is being able to see our data get analyzed, build a model, and test its accuracy. So I'm very excited to see how we can move forward with our data and continue to contribute to NeuroLex. Thank you so much. Are there any questions?
Yeah. So I think I really appreciate you guys bringing up the pitch and collecting data. I think this is probably the first tribe project that we had an IRB, collected data, and analyzed like an actual IRB approved study data in a tribe. So I think that's like a whole process in itself. So kudos to you guys for doing that. I'm curious, like, do you guys see ways to integrate your data set with other data sets that have been collected in depression? Just because Robbie and Maddie had like a lot of data sets that they collected and they didn't analyze yet. So do you think there's ways to combine and multiplex your data set with others that could perhaps synergize and you know, in ways that you could do right now as well?
Yeah, I think for sure, because our goal is always to look at as many features as possible that can improve like the accuracy of the model. So I think we've collected a lot of different like features to look at, and like I think our team would be happy to integrate that with other teams as well to just like analyze everything and make it as accurate as possible.
And the other question I had was, I think from the feature importances graph here, the loudness was the primary feature, the loudness SMA standard deviation falling slope feature. Mm-hmm. Like, what is it about loudness do you think is affected in depression specifically? Like, do you think there are microphone differences here that could potentially be attributable to the loudness as opposed to depression signal? Like, it could have just been like they're speaking closer to the mic or further away from the microphone. I'm just curious your guys' thoughts there on why that feature is so high and if there's any bias there.
So when I was actually, okay, I was just going to reference a study that made me look into like loudness and voice features in the first place, and they're talking a lot about how there's a difference between the way that individuals who are depressed and not depressed like express their emotion, and like one of the ways was through loudness. Like you can just like hear that in the way, and I'm not sure exactly like what it is about it, like whether it has to do with like confidence or like purely based on like a voice feature, but it's like really interesting. It's been expressed in a lot of different articles, so I'm glad that it was picking up that signal.
Yeah, I was essentially about to say the same thing. Like there's a lot of studies that show that in individuals who are depressed, there's a difference in like volume and how they speak and how they express different things when they're speaking. So that's why we wanted to look into that.
Interesting. Yeah, I was just curious. And also the pause speech ratio is in that chart in the top 20 features. We saw that in the MHA study as a really significant feature. So it's good to at least see that in the graph. But cool. Does anyone else have any questions for them? I think they're the last group. So we're like right on time, which is pretty rare to finish all perfect time. So 1 hour. If not, I really want to thank everybody for being a part of the tribe. I think you guys have all done great work here, and really excited to continue working with you guys in various capacities in the next phase here. And we're going to take a 1 hour break, judge some of these demos, and I'll announce all the winners over Mattermost. If you guys have any questions, comments on the judging process, how we came about it, we do have rubrics and stuff we're going to use. So we're always happy to give feedback and answer any questions you might have about the process. So, yeah, thanks again, guys, and really appreciate you for being a part of our journey as well. I consider you guys a part of NeuroLex just as much as any one of our team members. And yeah, looking forward to judging here and and working with you guys moving forward. So I'll stop the recording.